All right, let's get started. So today I'm going to talk about how to count carbon. This lecture may be familiar to some of you who have taken my life cycle assessment course, but I've changed it a little bit to really try to understand why certain amounts of CO2 are emitted from different sources of carbon-based fossil fuels. All right, so to begin with, let's just look at the carbon budget, where it's coming from. This is a little bit of recap from last time. So here is the perturbation of the global carbon budget for the last 150 years or so. And in the way back time, it was mainly just due to cutting down wood and burning it. And then around 1857, oil was discovered and coal was already being burned. And the heat engines were becoming more and more efficient with the new Cummins Watt engine. And so we started burning fossil fuels to power locomotion and to pump water around. And so here, oil and coal really began to take off. And now we're using all sorts of other fossil fuels, including gas at the end here. There are also sinks. Again, the main sink is the atmosphere. That's about 50%, but also some of the carbon is sequestered in the biosphere. So plants grow, take carbon out of the atmosphere. And then also the ocean is being slowly rendered more and more acidic as it incorporates more CO2 into its water. So I don't know why I have Elon Musk up here. It's just he understands this situation pretty well, and he's a celebrity, and so we listen to celebrities for some reason. But I like this idea. He says, well, I don't like it. It's actually horrifying. He says, we're running the most dangerous experiment in history right now, which is to see how much carbon dioxide the atmosphere can handle before there's an environmental catastrophe. And we're running the experiment in real time, and it's better to run experiments as models, but we're doing it with the actual Earth as our laboratory. Okay, so for today's lecture, again, it's all about figuring out how much carbon is emitted by burning different things. And so we're going to look at counting carbon, understand what Scope 1, Scope 2, Scope 3 emissions are, and then look at global warming potentials. So different greenhouse gases have greater or lesser abilities to trap infrared radiation. Methane on a 100-year timescale is about 28 times more potent per kilogram than a kilogram of CO2. So methane is a more potent greenhouse gas. So we'll look at global warming potentials for several different greenhouse gases. And maybe we'll do, if we have time, we'll do an example for the Stanford Linear Accelerator Laboratory on the Scope 1, 2, and 3 carbon counting or greenhouse gas accounting. But now I'm going to shift gears a little bit and get very technical or fundamental first principles, so we can think about where this CO2 comes from. So I need to share a different screen. Come on, Zoom, help me out. Share screen, this one, yeah. Okay, can you all see that white canvas? Cool. I have to move this Zoom window out of the way. All right, I have to find the pen. My daughters are always drawing with it. There it is. Okay. And they're always changing the settings to weird things. Just give me a pen. Fine point, that'll work. Okay, so we have some methane, right? That's CH4. We burn it with oxygen. And it turns into what? CO2 and some water. We can balance this equation. We have 4 hydrogens here. Well, okay, when you're doing stoichiometry, at least the only stoichiometry I care about, which is carbon emissions, you always just start with the carbons first. So 1 carbon makes 1 carbon, that's good. And then you go with the hydrogens because that's an input, right? Oxygen is freely available, so you do that last. So next we have 4 hydrogens. Here we only have 2 hydrogens on this side, so we need to put a 2 here. Now we have, lastly we do the oxygen. So looking at this side, we have 2 oxygens plus 2 more is 4 oxygens, so we need another 2 here. Now this equation is balanced, and the whole point of lighting this methane on fire is what? It's to make energy, right? To make heat and light. We can use that to boil water or spin a turbine or whatever. And so out of this reaction, we get Gibbs free energy, or the change in enthalpy, you recall from your chemistry classes. And for this reaction, we get 800 and, sorry, it's hard to write when I can't see where I am, 0.3 kilojoules per mole. So if you can't read my chicken scratch, that's 890.3 kilojoules per mole. And so that's pretty significant. It's actually kind of lower per mole compared to other fossil fuels, and that's just because it's a very small molecule. If you have something like octane, which is in your car's gas tank, that has 8 carbons and what would it be, like 10 hydrogens around it. So there's just more stuff to burn, and so it has higher energy per mole. But per unit mass, natural gas is pretty good because it's a very light molecule and releases a lot of energy. Okay, so we know how much energy we get, but how much carbon do we get? We have to look at the mass of these different molecules. And so if you look at methane, there's 1 carbon, which is 12 grams per mole, plus 4 hydrogens, which is 1 gram per mole each. Those are their atomic masses, right? Hydrogen is just a proton. And then that turns into CO2, which is, carbon is 12 grams per mole, plus 2 oxygens, which are 16 grams per mole. So this methane, which adds up to 16 grams per mole, turns into CO2, which is 44 grams per mole. All right, so far so good. What's its carbon intensity? This is going to be one of the most important things that we'll have to keep track of when we're doing greenhouse gas accounting, and that's how much carbon is emitted per unit energy for a particular fuel. And specifically not how much carbon, how much CO2 is emitted. So all these different fuels will have different carbon intensities, amount of kilograms per gigajoule or something like that of energy. So let's figure out the carbon intensity of natural gas or methane. And so we know how much carbon gets made, and we know how much energy gets made. Okay, so we have 44 grams of carbon produce 890.3 kilojoules of energy. But this is pretty ugly, right? That's not a nice thing that you would look up on Google. If you typed in the carbon intensity of natural gas, you're not going to get 44 grams per 890.3 kilojoules. So let's standardize this. So let's put it in terms of a megajoule, which is 1,000 kilojoules. Solving for x, we get x equals, I already did it before class started, x equals 49.4 grams per megajoule. So that's the carbon intensity of methane. If you look it up, it's usually going to be in terms of mega BTUs. Remember, that's the standard for natural gas. That's a cubic foot of natural gas is a mega BTU or an BTU. Don't confuse that with a therm. That's on your power bill. That's 10 to the 5 BTUs. So power of 10 less. So if we look at this in terms of mega BTUs, then we have to do a different ratio of proportion. So we have 49.4 grams per megajoule. So that equals how many grams of CO2 per mega BTU. A mega BTU, recall a BTU is 1,055 joules. So a mega BTU would be this megajoules, right? Because 1055 joules is a BTU, so mega BTU would be 1055 megajoules. All right, so rearranging this equation, solving for x, we get x equals 52 point-ish. And if you actually look up the table in Google and ask what's the carbon intensity natural gas, you get 53 kilograms per mega BTU. So even though we did all this math from very first principles, going from atomic masses and Gibbs free energy, we get the same answer that's in Google, and that's good, right? So science works again.
So,
Yeah.
that's carbon intensity or CO2 intensity?
CO2 intensity. And when I say carbon intensity, I always mean CO2 intensity.
Okay,
Yeah.
just checking.
Often you just see emission intensity or emission factor when you're looking around.
Okay.
Another reported value that you'll see on Google is 55.7 kilograms of CO2 per kilogram of natural gas. And we could rearrange all these kilojoules and kilograms and arrive to that same value as well. So what does this mean? It means that when we burn, if we get a mega BTU of gas, if we burn a mega BTU of gas, we emit 53 kilograms of carbon. Usually a person burns about a therm of gas a day in their house to keep it warm and to heat water. And so that means every day you emit about 5.3 kilograms of CO2 from your house for consuming natural gas. Any other questions about that? This isn't something you need to commit to memory or anything. I just want you to know that all these emission factors and carbon dioxide intensities come from fundamental physics and chemistry, and it's not magic. You can figure this out, and you can trust the numbers that you see on the internet. All right. So on Canvas, stop share. Share a different screen. Internet. Oh. My solar panels are going awesome right now with all this sun, so I've been geeking out on that. Making like 5 times as much energy as I'm using right now, which is cool. But that's not why we're here. So on Canvas, underneath, well, first off, after the first lecture, I posted a link to the video that's been recorded. I suppose all of you don't need that since you're here in person, but they'll be available for your review. Otherwise, just use the slides. And then under this lecture, carbon accounting, there's some fact sheets and tools that you'll find useful when you're doing your analysis later in the quarter and throughout the rest of your life, because you'll all be good energy and carbon accountants. And so I wanted to look at a few of those. So here's EPA emission factors for fuels. I have that over here somewhere. Yeah. Okay. So this is way too detailed, but you can look up different things. So let's go to where we were, natural gas. Natural gas per SCF? I don't know what that means. Standard cubic foot? Standard 100 cubic foot? Well, this is the number we're interested in, right? So kilograms CO2 per mega BTU. That's 53.06. That's what we just calculated. So again, math works. And so here's this lookup table. You can look at it for several different fuels. So if you're just burning wood in your wood stove, 93 kilograms of CO2 per mega BTU. So it's more carbon intensive than natural gas. That makes sense for a couple reasons. There's more carbon in the lignin that the wood's made out of The ratio of carbon to hydrogen is higher in wood. And also there's a lot of water in wood, so you don't get as much energy per unit carbon emitted because you have to boil water instead of just making heat. The latent heat of evaporation takes some of that energy away. Here's coal. So you start to see this trend. The more carbaceous, the more carbon rich the fuel is, the higher kilogram, so CO2 per megabtu. When you burn hydrogen, you get energy too, but when you burn hydrogen, its product is water. And so that's why natural gas is the cleanest fuel, because you're getting a lot of energy from the hydrogen in addition to the carbon. You can look at different things like motor gasoline, 70 kilograms per megabtu. Compare that to diesel. Is that up there? Crude oil, distillate, motor gasoline, other oil, petrol, biodiesel, motor gasoline, 70. I can't believe that. Are these the diesels? Yeah, these are the diesels. The distillate fuels? I forget. Diesel has another name that I'm not finding right now. But diesel, the point of this, diesel is a little bit more carbon intensive than gasoline, and that's because, again, there's more carbon to hydrogen in these diesel fuels. So here's one lookup table that you can use. Another tool that's available is this. Do I have it open? No, I don't. If you look on the Canvas page, there's something called the stationary combustion tool, and it's pretty cumbersome, but I'll show it to you. I don't really use this, but it's from the Greenhouse Gas Protocol. Let me share that screen. Stationary combustion tool. All right, get this out of the way. So here it is. It's this. It's from, again, Greenhouse Gas Protocol. This was a group developed in the 90s to account for all these carbon emissions. It's a .org, so it's a nonprofit organization. It's a collaboration worldwide. I forget where they're based. I think in the Midwest somewhere. But they produce all these tools and documents to help account for carbon. And so, again, this is kind of cumbersome, but the way it works is you go to the spreadsheet. I don't know what all this stuff is. You can geek it with your own values if you want to update it to 6th assessment report when it comes out. I don't know. But here's the spreadsheet. So you go, okay, I want to think about a gaseous fossil fuel, and I'm looking at natural gas. So it has so many different fuels, but the first step, you take fuel type and you say, is it solid, liquid, or gas, or biomass, or I don't know what my fuels means. If you invented something, or let's just leave that alone. So natural gas, so the amount of fuel, let's say we're burning 1, and we're going to burn 1 megabtu, right? And 59 kilograms, that's wrong. So all these are in metric tons, tonnies. 59, that's wrong. So what happened there? It's using the lower heating value instead of the higher heating value. So when you burn something like natural gas that has a lot of hydrogen, if you use the lower heating value, you say, well, some of that energy was lost to evaporate the water that you produced by combusting the natural gas, and that energy was just lost when you consume it. So this would be something like burning natural gas in your house to heat your house. That's why if you see a natural gas furnace going at a house in your neighborhood, you see that poof of steam coming out the side of the house or the top of the house. So that hot water, you don't get that heat energy. It's just lost. So the carbon intensity goes up. But if you're burning it in a power plant, then you can still use that steam to spin a turbine, and so you can use that thermal energy. So if we go on a higher heating value basis, then you get that lower carbon intensity, or another way of saying it, you get more energy out per unit carbon emitted, CO2 emitted. So here's again that 53 kilogram number that we calculated. So here's another tool, a stationary combustion tool. It's available on Canvas. You can type in whatever fuels you want. Let's see if they have okay, charcoal for your barbecue. Let's burn 1 kilogram of charcoal. So to run your barbecue with a kilogram of charcoal, make a hot dog or something, you emitted 3 kilograms of CO2. So how did 1 kilogram turn into 3 kilograms? It got a bunch of extra mass from the atmosphere, right? It pulled oxygen out of the atmosphere, combined it with that carbon, and now it's heavier. Make sense? All right. Back to the lecture. Share a screen. Is this it? I'm sharing the presenter view. How painful. This one? Yeah. Okay, cool. Okay, so let's look into what scope 1, 2, and 3 is. It's determining where the carbon is emitted along some life cycle chain. So we have to talk about life cycle assessment really quick. I don't need to tell you why we count carbon. That's the whole point of this class. Where's my little pointers? Laser pointer. All right. Yeah, again, a lot of these resources come from the GHG Protocol Initiative. It's ghgprotocol.org. It's part of the World Resource Institute. Again, multiple countries, multiple companies, all working together to standardize greenhouse gas accounting. And here's a report with a very 90s looking cover. All right, so scope 1, 2, and 3. Where did these emissions come from along the life cycle chain? So we have to know a little bit about life cycle assessment. I've used this chart in ENRG 101 to demonstrate where energy and carbon may be emitted along the things. Normally I do this interactively, but I'm not going to force you all to talk because we're on Zoom. So you need energy to harvest these raw materials. You need to grow peanuts in the ground. You need to grow cane somewhere. You need to grow different plants that make oils somewhere. And so those farming activities will require energy, require diesel in the equipment. So carbon will be emitted when we're making raw materials. Carbon will be emitted when we're making all the materials for packaging the peanut butter. Carbon will be emitted when we actually begin to process these raw materials into peanut butter itself. So we have to roast the peanuts, grind them, mix it with the other products that go into it. We have to manufacture these different packaging products, and then we package them up, ship them to a store. That's going to emit a lot of carbon as the vehicles and trucks are driving around. It's then shipped to a retailer, and then it's consumed. Some people put it in the refrigerator. I don't personally, but that's going to consume more energy. And then finally you throw it in the alley behind your house and another truck comes and takes it away. That's going to emit more carbon. So carbon was emitted throughout this entire life cycle of something as simple as a jar of peanut butter. So how do we count all this and how do we categorize it? Well, GHG protocol came up with this scope 1, scope 2, and scope 3 reporting protocol. And here's a picture of that. So right now, companies in states like California and nation states like Germany are required to report their carbon dioxide emissions, and more in Washington state as well, especially with our 2045 mandate. But they're usually only required to do scope 1 and scope 2. Scope 1 is things that are actually smoking at that factory or store or corporation. So burning natural gas in a building will emit CO2. That would be a scope 1 emission. It's happening on site. Another scope 1 emission would be a company's vehicle fleet. So that's, even though the vehicle might not be emitting the carbon directly on site, it might be somewhere around Bellingham or somewhere else. It's vehicles owned by that company that are emitting CO2. So scope 1 is emissions on site in buildings and emissions associated with that company's vehicles. If it is my household, scope 1 emissions would be whenever I turn on my radiators and natural gas is consumed, or whenever I fire up my wood stove, that'd be a scope 1 emission. And whenever I drive my car somewhere, that'd be a scope 1 emission. Scope 2 is all electricity. So what is the carbon intensity of the electricity that's going into your house or your company's building? So you measure how much electricity you consume at your house or your building, and then you look up the carbon intensity of your power grid, and that would be your Scope 2 emissions. We'll go into that a little bit more later. And so again, most policies require Scope 1 and Scope 2 reporting, not Scope 3. Scope 3 is a lot harder to do. Scope 3 is the life cycle chain. So that would be, for my house, for example, if I bought some dog food for my dog who's asleep right there, I guess she would be emitting some CO2 whenever she breathed, but that might be a Scope 1 that nobody ever counts. But the Scope 3 emissions associated with that dog food, making the salmon and sweet potatoes somewhere in BC and then shipping it down here, that's not counted usually. But those would be Scope 3 or life cycle emissions associated with operating a house or a factory. And we count not just CO2, but all the greenhouse gases that may be emitted. So here are some other greenhouse gases like CO2, sulfur hexafluoride, which is really, really potent. That's that gas that, you know how helium makes your voice high? Sulfur hexafluoride is an inert gas that you can breathe in, and it makes your voice really, really deep because it's really dense. But you got to be careful because it's so dense, it'll displace the oxygen in your lungs, and you won't be able to breathe, so you have to like go upside down and breathe it all out again. Neil deGrasse Tyson does it all the time. There's different funny videos with it. Methane, nitrous oxide, or laughing gas, hydrogen HFCs, what are those? Hydrofluorocarbons. Those are pretty much illegal, and PFCs, I don't even know what those are. Different kinds of refrigerants. But these are also very potent greenhouse gases. All right, so talking a little bit more about Scope 1 versus Scope 2. And this is another thing we need to be a little careful about, that we don't double count these emissions. It depends on, it's kind of relative, right? So here's a consumer at a house. They emitted 90 tons of CO2, but it's all Scope 2 emissions associated with the electricity that they were consuming. So this would all be Scope 2 emissions for the consumer, but from the perspective of the power plant, these wouldn't be Scope 2 emissions because it's not from the electricity required to run the power plant. These would be Scope 1 emissions because it's coming out of the smokestack of that power plant, out of the stack. And so it'd be a Scope 1 emission for a power plant, but a Scope 2 emission for the consumer. The consumer would also be responsible for these emissions too that were required to deliver that electricity to the consumer. Or this is associated with line losses. We'll go into that more later. The actual coal mining not power plant, but the coal mine has big machinery operating on diesel, and so it's emitting 5 tons of CO2 directly. Those would be Scope 1 emissions because it's associated with the vehicle fleet or their operations. So that's a little bit more with Scope 1 and Scope 2. This was an example from GHG protocol for a corporation, and so their Scope 1 emissions again would just be on-site combustion and on-site vehicle use, or vehicle use for their fleet. We wouldn't count the actual commuting from the employees because that doesn't have to do with company business or corporate business, and so this would be a Scope 2 emission, or a Scope 3 emission. So it's still like CO2 being emitted for the sake of the company, but it's not direct company business. It's not company cars. So this would be Scope 3. Most everything is Scope 3, right? So all the capital equipment, business travel, assets, pencils, papers, computers, everything that's going into this corporation would all be life cycle assessment Scope 3 emissions. Again, Scope 2 is pretty simple. It's just whatever electricity is used in the corporation, so that's in green here. And yeah, so most everything's scope 3, and it's the hardest to count, and most people don't count it, and a lot of companies are not required to count it. But it's becoming more and more important as we try to, again, knock down carbon emissions. So we have that big pie graph where the emissions coming from. Obviously, transportation is a huge one. That'd be scope 1. And electricity generation, scope 2, would be a big one. But more and more, we need to concern ourselves with the carbon associated with stuff, and that would be all scope 3. All right, basics of carbon accounting. We already looked at this a little bit with playing around with the carbon emissions and carbon emission intensity, CO2 intensity of burning natural gas. So how do we do it for any fuel? It's pretty simple math. You just say how much fuel am I burning and what is the carbon intensity of that fuel. So burn a megajoule of natural gas or a mega BTU of natural gas, and I multiply it by its carbon intensity, which is what, like 53 kilograms per mega BTU. And now I know how much CO2 I got emitted from doing that natural gas. And so the amount of fuel consumed, that's something you would get from your client if you were being a consultant trying to calculate the carbon for something, or for the sake of this class, if we're looking at the emissions from the city of Bellingham, or lack of emissions due to COVID-19, or emissions of Huxley College and Environment, we would say, well, how much fuel was used, then multiply it by its carbon intensity. Quick note again, we talked about this last time, factor 3.66 difference between carbon and CO2, so be careful with that. Greenhouse gas emissions are generally expressed in terms of CO2, but the fossil fuel companies usually report it in terms of just C as carbon, because it makes their books look, a factor of 3 to 4 better than they truly are. So just be careful with that factor of 3.66 when you're doing this kind of analysis. All right, so here's a few carbon contents of fuels. We already looked at that huge list from the EPA and the GHG stationary combustion tool, but here are the ones that are most common, you'll most commonly use. And so there's coal, bituminous, that's like the coal from Powder River Basin, and that's most all the coal we burn in the United States. Diesel oil, I really should have gasoline up here, and then natural gas. And so here's kilogram CO2 per gigajoule or per mega BTU. You can also do it per kilogram of fuel or gallon of fuel. That's pretty standard. Yeah, so usually liquids are reported in gallons. Most fuels are reported in terms of their energy content that we use for electricity, like coal and natural gas. And you can see that their carbon intensity, or their emission intensity, their carbon dioxide intensity, is different for these different fuels, and it's directly associated again with their carbon to hydrogen ratio. You get energy and light from burning hydrogen in an oxygen environment, and you get energy and light from burning carbon in an oxygen environment. The product of burning hydrogen is water. It's not a greenhouse gas. Well, it is, but it just falls out as rain right away, so it's not something we need to keep track of. And then CO2 you get as a result of combusting carbon. So the higher carbon to hydrogen ratio, the more carbon intensive, CO2 intensive that fuel is. So natural gas has a 1 to 4 carbon to hydrogen ratio, and so it's much less carbon intensive than coal, which has a near 1 to 1 carbon to hydrogen ratio. And again, that's why CO2 emissions for the United States of America went down this last decade, and it's because we switched from coal electricity to natural gas-based electricity. But we only got halfway there, so we need to switch from coal now to renewables to get it down to zero, or near zero. Okay, so let's look at scope 2, making electricity. It gets a little more complicated. We'll spend more time on this in our electricity lecture, but this is just the fast and loose. So the CO2 intensity depends on the carbon content of the fuel and the fuel efficiency. So how many kilowatt hours do you get per gigajoule? You put a gigajoule of fuel into a coal power plant, and you're only going to get 0.33 gigajoules out, because 2/3 of that energy just goes up the smokestack, due to the the efficiency of the Rankine cycle. Natural gas power plants are about 44% efficient combined cycle. That's where you take a Brayton jet turbine for the natural gas and use the exhaust to fuel a Rankine, a boiler turbine. They can get up to about 60% efficient for natural gas. So the CO2 emissions depend on what you're making. So this would be electricity, in this case, energy service. The fuel carbon, so the carbon intensity of the fuel, which we looked at last slides. And then you divide that by the fuel efficiency. So efficiency is always a number less than 1, and so that slowly gets, as the fuel efficiency goes down, the total emissions go up because you have a number less than 1 in the denominator. This is a little janky. We can look at some more examples in a sec. All right, but in general, to reduce emissions, improve fuel conversion efficiency, lower the carbon content of the fuel itself, renewables are near zero. Well, they're zero for scope 1 and 2, but they're not zero for scope 3 because it still takes carbon and energy to build a solar panel, for example. Or you can improve end-use efficiency. So that would be the direct way to do it, but people have already done all this math for us, and you wouldn't even be able to do that method in the last slide unless you called like Puget Sound Energy, for example, and said, well, what is the efficiency of Incogen power plant downtown, and how much fuel do you use, and blah, blah, blah. Then you could get its carbon intensity. Instead, you can just use this EPA.gov Energy eGrid website, and it has a big Excel file that has the carbon intensity of every power plant in the United States. And then they bin them all based on balance authority. So we're in the Puget Sound Energy balance authority, so you can look at the average carbon intensity or CO2 intensity of PSE's grid mix. And so that's what you would do in this case.
I'm not sure.
So we'll explore eGrid in a homework pretty soon, and it'll be familiar to, again, those of you who've taken my life cycle assessment course. But that's, again, not for a little while. But this is the resource I use. I've found that if you actually look at the internal reports from different balance authorities, they're often a little bit higher because the actual balance authorities include things like methane leakage. And so, average methane leakage for U.S. gas grid is about 2.8%, and that significantly increases the greenhouse gas emission, or CO2 equivalent greenhouse gas emissions, because methane's so potent. But everybody uses eGrid, and to keep the playing field level, we should use eGrid as well, and just wait for eGrid to update. They update every 2 years, and hopefully they'll begin to include like methane leakage in future releases. So again, you can look at, with eGrid, you can look at specific balance authorities like Puget Sound Energy. That you can actually just go all the way down to a power plant. The next level is balance authority, and then the level beyond that is states. They bin it by states, and then the level beyond that is I forget what these are called. Sub-regions or something. These are big regions of power grids that work well together. I'm not an economist, like these imbalance markets or something. They share a frequency. Texas has its own frequency, so they don't share with anybody. That's why they're separate, even in this massive balance authority or massive sub-region map. And so, yeah, each one of these regions have different emission intensities, scope 2 emissions for their electricity. So in this massive western region, western interconnect, so this all shares the same frequency, so we're able to trade, buy and sell electricity to each other. So often, Washington State's selling electricity to California. On average, this entire region emits 540 grams per kilowatt hour. That's about what natural gas is, actually. Natural gas is like 490 grams per kilowatt hour. So this is natural gas, maybe a little bit of coal, and that's why it is what it is. There's more coal in the Midwest, and so that's why it's higher. A lot of coal in the South too, so these are slightly higher than us. Our grid is about 200 grams. Puget Sound energy is about 200 grams per kilowatt hour, and it's far less than natural gas average, and that's because we have so much hydropower. But it's really quite a shame if you look at, just a county below us, Snohomish PUD, and I guess that's 2 counties below. Seattle City Light, they're all near zero. Jefferson County, near zero, and that's because they rely solely on hydropower. PSE still has a lot of natural gas in their mix, and I think still 1 coal-fired generator left that they just decommissioned some of them. Okay, so that's an intro to scope 2 calculations. And so if you want to calculate the emissions associated with electricity use, just use eGrid. If you want to go back into the nitty gritty, then you have to consider line losses and the efficiencies or heat rates of the fuel. So the actual emissions from electricity depend on the carbon content of the fuel, so coal or natural gas, metric tons of CO2 per gigajoule. You multiply that by the heat rate. That depends on your power plant. So this is like the inverse efficiency. How many gigajoules do you stick into that power plant? How many gigajoules of coal or natural gas do you put into the power plant to get a megawatt hour of electricity out? And then you multiply it by the distribution losses. And so that is usually it's your megawatt hours divided by 1 minus line losses. And on average in America, line losses are about 7%. I don't know where that number comes from. I've asked people like, well, surely it must be different if like the power plant's only 1 kilometer away versus 1,000 kilometers away. You'd think there'd be more line losses, but everybody just says 7%. So that's what we use. And so that factor is on the denominator. 1 minus 7% is 0.93. And so that's a number a little bit less than 1. And so that increases the emissions, because if you want to use a kilowatt hour or a megawatt hour at your corporation or your home, you need more than a megawatt hour or a kilowatt hour at the electricity generation plant, because 7% is lost along the way. And so your emissions that you're responsible for is not just the electricity you consume at your house, it's electricity you consume at your house plus electricity that was lost along the way trying to get to your house. Make sense? Okay. I've rearranged some of these terms for putting it in terms of efficiency. And so again, heat rate is a measure of thermal efficiency. It's just the inverse of it. If we put it in terms of efficiency, then you have to rearrange heat rate. So heat rate is in gigajoules per megawatt hour, but efficiency, remember, is unitless. So it needs to be gigajoules per gigajoules or megawatt hours per megawatt hours. And so to get megawatt hours per megawatt hours, we take a gigajoule, which is 1 billion joules, and we have to get it up to a megawatt hour, which is 3.6 billion joules. Recall that a kilowatt hour is 1,000 joules per second. That's what a kilowatt is, multiplied by 3,600 seconds. That's how many seconds there are in an hour. And so you have this factor of 3.6 when you're climbing from any step. So like gigajoule to megawatt hour or megajoule to kilowatt hour, you have to multiply by 3.6. So to make this equivalent, we have 3.6 gigajoules per megawatt hour. So that'd be the generator efficiency. So if you don't have the heat rate for a particular generator, you can use the actual thermal efficiency. Let's do some examples real quick so this starts to make some sense. So here's a gas-fired unit. It has a heat rate of 7,700 BTUs per kilowatt hour. So if you want a kilowatt hour of electricity from a natural gas plant, you have to put in 7,700 BTUs of natural gas, or 7.7 mega BTUs per megawatt hour. Multiplying by 3.6, we can see that yields about 44% efficiency if we invert that and multiply by 3.6. And so the CO2 content of electricity at 44% efficiency with, I guess in this case, 8% transmission and distribution losses would be 8.1 gigajoules per megawatt hour. That's the heat rate, multiplied by the carbon content of the natural gas, the CO2 content, which we did at the very beginning of class, so 50.5 kilograms of CO2 per gigajoule. Then you divide that by 1 minus line losses, so this is a number less than 1 in the denominator, so it's going to grow the amount of emissions. And then this is just a conversion factor going from kilograms, which was our stated emission intensity, to metric tons, which that's what carbon is always reported in formally. So we can see that we have 0.44 metric tons of CO2 per megawatt hour. And don't get tripped that this equals the efficiency. That's just a coincidence of mathematics. You can't just take the efficiency of a power plant and say that's what its carbon content is. Comparing that with a coal-fired power plant, its heat rate is much larger. Does that mean it's better? No, it means it's worse. It means you have to put in more BTUs per kilowatt hour. You have to put in 10,400 BTUs of coal to get a kilowatt hour of electricity. Again, if we do some mathematics with that 3.6 conversion factor, that we can see that that heat rate corresponds to 33% efficiency. The CO2 content, the electricity at 33% efficiency and 8% line losses are again that heat rate multiplied by the carbon intensity of the coal, 91.3 kilograms of CO2 per gigajoule, divided by 1 minus line losses, conversion factor to metric tons, and we can see that the carbon content of the CO2 is over a factor 2 greater than that of the natural gas at 1.09 metric tons of CO2 per megawatt hour. So what makes coal worse? There's 2 reasons. Am I even seeing chat anymore? How do I see chat? More chat. All right, well, I'll just tell you why. Maybe you already know this and you're just being shy. Coal is worse because there's more carbon content per unit fuel, right? The carbon intensity is twice as high, but that's not the only reason. That's the obvious reason. The other reason is it's not as efficient, right? So more the energy you get out of that coal goes just directly into the atmosphere as waste heat and doesn't turn into electricity. So coal is worse than natural gas for 2 reasons. Higher carbon content in the fuel, less efficient ways of generating electricity. Okay. Let me get back over here. All right. Biomass. So often biomass isn't considered part of the carbon pool because when it's used for combustion, because the idea is that the forest is always being regrown. And so there's different biomass electricity generators all over the place. There's one they're thinking about building on the Big Island of Hawaii right now. There's several in California in the Central Valley, and it burns things like pistachio shells and almond shells for different agricultural waste. They even burn Christmas trees different times of the year, I guess one time of the year. And those aren't counted as CO2 emissions because that CO2 recently came out of the atmosphere to make those feedstocks. But if a forest is being depleted, I would make the case that we should count those emissions. And land use change, certainly we should count. If we clear a forest to grow cows or grow palm oil, that would be something that would need to be accounted for. Okay, so now we're going to get into global warming potential values. Let's take a 5-minute break before we do this. Sound good?
What's up, Kip?
Man, it's such a nice day out there. I miss campus. Like, spring quarter is always the best. But all right, global warming potential values. So there's many different greenhouse gases. They have different propensity to absorb infrared radiation and re-emit it in all directions. It all has to depend on the structure of the bonds of these different molecules. I forget the formal name for this physical model of molecules, but you can picture the different atoms in a molecule as being attached by springs, and they vibrate back and forth. And that quantized vibration can be related to the energy levels in photons. And so infrared photons stimulate the vibrational modes of these different greenhouse gas molecules and allow them to absorb that photon in that vibrational motion and then re-emit the photon sometime later. And so that's basically how greenhouse gases work at a quantum level. And the ability to absorb photons, infrared photons, and re-emit them depend on the molecule and their structure, and they have different global warming potentials. Now, the main global warming gas we're concerned about is carbon dioxide, CO2. And so what global warming potential values do is allow us to relate all the other molecules that are greenhouse gas molecules to CO2. And so we can come up with this term called CO2 equivalent. And that way we don't have to say like this power plant emitted this much methane, this much CO2, this much nitrous oxide, et cetera, et cetera. We can just bin it all together and say this power plant has these CO2 equivalent emissions. 1,000 kilograms, it's CO2 equivalent per megawatt hour, for example. All right, so the way that these are calculated is you look at the radiative efficiency, that's this AI term, of this gas species you're interested, like methane, and then you look at the concentration as a function of time, and you integrate that over time from the time it was released, TR, to the time horizon you're interested in. Are you interested in what it looks like 25 years from now, what it looks like tomorrow, what it looks like 100 years from now? You are not responsible for this in the class. I just want you to know where all this comes from. And so in this particular graph, we have, I'm trying to look around my camera, we have carbon dioxide in this line, and this is fraction of carbon dioxide remaining in the atmosphere over 500 years versus this HFC refrigerant. So this HFC refrigerant decays much more rapidly than CO2. CO2 is pretty inert in the atmosphere. It slowly gets sequestered in the ocean, and it slowly gets taken up by the biosphere and slowly turns into calcium carbonate when it mixes with rain and dissolves rocks. Okay, so point of this is we compare how strong the gas is as a greenhouse gas and how much of that gas is in the atmosphere as a function of time, and normalize it to CO2. And that way we can say, is it stronger than CO2 or less strong than CO2 at some time horizon? You can also use radiative forcing, which is just a function of radiative efficiency and gas concentration. These are all equivalent terms, again, integrated from time of release to target horizon. Okay. So here is methane. Global warming potential, it's a function of time horizon. This is from assessment report 4 down here. And so 20 years, its global warming potential is 72. That means it's combination of radiative forcing and concentration at 20 years out, 1 kilogram of CO2 or methane released into the atmosphere will, as far as global warming is concerned, is equal to 72 kilograms of CO2. So 1 kilogram of methane 20 years out is 72 kilograms of CO2. The science has become more accurate over the last, decade, and so by the time we got to assessment report 5, that 20-year global warming potential value for methane is now at 84. So 1 kilogram of methane emitted 20 years later, it looks like 84 kilograms of CO2. Over time, methane decomposes. UV radiation cracks that carbon and hydrogen apart. The hydrogen finds an oxygen molecule, makes water. Carbon usually finds an oxygen molecule and makes CO2. So methane kind of hits twice. It's not only stronger initially, it's better at absorbing and re-emitting infrared radiation. It decomposes into CO2 and then hangs out for a long time. But it decomposes relatively quickly, and after 100 years, the global warming potential of methane is only 25 kilograms of CO2 versus 72 at 20 years, or 28 in AR5 versus 84 in 20 years. So we should be using AR5 in this class because it's the most recent information. Generally, society and carbon accounting and policymakers always use this 100-year global warming potential value. I'm not exactly sure why. There's arguments to be made for both cases. If the people argue for the 100-year timescale because this is what's going to be important for future generations and is a more like environmental or earth-based perspective. People argue for the very shorter time horizons because that's actually what we'll feel in the near term. And then even climate scientists actually argue against this 20-year horizon because they say that we'll try to say that it's worse, and then I don't know, some political or sociological arguments. Point being, most people use this 100-year time horizon both in scientific and policy literature, so that's just mainly what we'll be using in this class too. Okay. So this is from AR4. This is the 20-year, 100-year, and 500-year global warming potential values for several gases. CO2 is 1, 1, and 1, because if you go to this integral, it'd be CO2 over CO2. And so this would be 1. It would be some number over the same number. 10 divided by 10 is 1. And so that's why CO2 is 1 throughout. It's the normalization constant. Here's methane. Slowly goes down as it decomposes into CO2 over time. Couple things to point out. So sulfur hexafluoride is one of the worst gases, and so it's 16,000 times more potent than CO2 in the 20-year, and even more so in the 100-year. How does it get more potent over time? That doesn't make any sense. Is it growing? What's happening? No. You think back to this equation, right? So this is all in relation to the concentration of CO2 over time. So it's saying that the concentration of sulfur hexafluoride, it remains in the atmosphere. It's inert, right? So it doesn't decompose, it doesn't weather, it doesn't get absorbed by the ocean. So it hangs in the atmosphere much longer than CO2 does. So its relative forcing to CO2 over time increases because its concentration stays steady, whereas CO2's concentration goes down over time. So the sulfur hexafluoride is really bad stuff. It's used in chip fabrication, very sensitive lasers and electronics and that sorts of thing. Because it's really heavy and it's inert, what they do is they fill a chamber with sulfur hexafluoride to displace all the atmospheric air, the nitrogen and the oxygen, to make a very stable environment for these different sophisticated electronics. That's what it's for. Here's a couple refrigerants. They're now really high global warming potentials. So the amount of emissions from these species of gases are really low, but their GWP, their global warming potential, is really, really high. And so we certainly need to pay attention to them. I think on Canvas, I put a link to the AR5 stuff. How does Zoom work? Share screen, Canvas. Yeah, so it's somewhere up here. Yeah, global warming potential values from February 16, 2016. So this is what we'll use for the class, this PDF here. There's a little, this is the GHG protocol footprint. Here's that stationary combustion tool, emission factors that we already saw. Yeah, so this is basically all the tools you'll need to count carbon. Stop share. Share screen. All right. So how do you actually do this math? It's really easy. You just take how many kilograms of methane got emitted. So say you emitted 2 kilograms of methane, and you're going to use the 100-year time horizon. How much CO2 do you have? You take the 2 kilograms, you multiply it by the GWP, it's 25, and that equals 50. It means 50 kilograms of CO2. The math is that easy. You don't have to worry about those integrals or all that other complicated stuff. You just take how much mass of the gas you're interested in was emitted, multiply it by its GWP, and now you have its carbon dioxide equivalent, or CO2e. So for methane, 2 kilograms equals 50 kilograms CO2e. Yeah, this is just showing how the science has changed over time for these different gases. We're continuing to think about these things and update them. All right, so this is what I just said. Equivalent CO2 from non-CO2 GHG emissions. The equivalent CO2 emissions depend on the emissions of the gas multiplied by the global warming potential of the gas. I don't even know if I want to talk about this. This is like a weird accounting thing that oil and gas companies do. So CO2 equivalent of fossil methane GHG reduction. So when you produce oil, you produce gas along with it. The gas is lighter. It's sitting on top of the oil in the reservoir. Oftentimes it's unprofitable to liquefy that natural gas and ship it somewhere, especially when you're somewhere super remote, like the north slope of Alaska or in Siberia or something like that, or the middle of the Gulf of Mexico. And so they flare that gas, and that means they just light it on fire. And they say they're doing something good for the environment. And technically they are, because if they just let that methane go straight into the atmosphere, it'd be, 86 times more potent on a 20-year time basis. And so they say, well, we actually turn that methane into CO2, and so we can calculate our equivalent reduction. So methane reduction from flaring, a metric ton of methane, you take the molar mass, the GWP of the methane, and then subtract the ratio of molar masses, because you're turning the mass of methane into CO2, and say, I actually saved 8.25 tons of CO2 equivalent by burning that methane. I took that methane, which is 21 times more potent, but of course it turns into CO2, so I have to subtract the amount of CO2 that it turns into to say how much I actually saved if I'm an oil company. Or in terms of assessment report 5, by flaring methane, they saved 25.25 CO2 equivalent emissions because they didn't allow that methane to go up there. I think it's pretty cheap to say that, like, oh, I'm saving the environment by burning methane in the middle of nowhere, but technically it's correct. Okay, big common sources VARs for greenhouse gas accounting. The main one is confusing carbon with CO2. Another one is confusing CO2 with CO2 equivalent. Short tons versus metric tons. Remember, a short ton is 2,000 pounds. A metric ton is like 2,200 pounds or 1,000 kilograms. Stupid labels like BTU and capital M for megajoule means a million. for BTU means a million. Higher heating value versus lower heating value. This can cause like a 10% difference in the emission factor, especially for natural gas. The more hydrogenated fossil fuels, the ones with more hydrogen, because they make more water. Power plants always use HHV, and that's what you'll see usually. There's different types of coal and fuels and diesels and all sorts of things. I don't know if any of you are ex-military. I'm not, but there's tons of different diesel fuel types for different military applications, like Humvees versus tanks versus helicopters, etc. Different GWP values depends on the assessment report and the time horizon. Again, in this class, we'll mainly use assessment report 5 and the 100-year time horizon. Scope 2 intensities for electricity. Did people account for transmission and distribution losses, this 8% or 7% loss, etc.? Are they using average emissions or the marginal emissions of the generator? So, different times of day, the actual carbon intensity of the grid could be very different than the average carbon intensity. So like in California at 2 p.m., the carbon intensity is super low because all the solar panels are going. Right at like 6:30 p.m. as the sun is setting in Los Angeles, carbon intensity goes way up, and because they're turning on all these natural gas generators to feed all the air conditioners. And right when you turn a natural gas turbine on, it's actually not very efficient at all because it's getting warm. Think of at an airport, you're sitting in the airplane before it's going to take off. They fire up the engines, the turbines, which are natural gas turbines for all intents and purposes. You can smell all that exhaust if you're sitting behind the wing, and that's because the engine isn't very efficient yet. And so these marginal emissions could be quite higher. And then there's fuel chain emissions. So this is so-called like well-to-wheel emissions. So there's emissions associated with producing coal, gas, and oil. Are those being accounted for? Those are scope 3, right? They're deep in the life cycle. All right, before we go, let's go through one example. This is a national lab near Palo Alto, Stanford Linear Accelerator Center. So this is one of these particle colliders. And here's the greenhouse gas footprint data. This is analysis done by Joel Swisher. He's a professor here. He's the director of the Institute for Energy Studies. And so these are all the things he bookkeeped. Here's the information he received when he did this analysis. Electricity use is 333,000 megawatt hours. He assumes 8% T&D losses. California grid emission factor at that time was 328 kilograms CO2 per megawatt hour. On-site fuel use, so this would be scope 1, right? The grid would be scope 2. On-site fuel use is 97 million cubic feet of natural gas, so that's probably for heating and cooling. Transportation fuel use, so all the little trucks on lab, 50,000 gallons of diesel fuel used. They do have sulfur hexafluoride for some of their lasers, so that's 2,000 kilograms of sulfur hexafluoride used each year. They have refrigerants, 5,000 kilograms of HFC 134A used per year, and another chlorofluorocarbon or whatever they're called, 800 kilograms of that. It's a different refrigerant. So what's their total greenhouse gas footprint? Let's count the carbon and the other gases. It is located on the same land that Stanford is on, and so as reference, we can see that all of Stanford emitted 150,000 metric tons of CO2 that year, mainly associated. Stanford has a natural gas cogen plant on site, so it makes electricity, and it actually makes ice because it's in California. So they don't make heat like our steam plant does on our campus. They make ice that they use to run air conditioning throughout campus. All right, so electricity. Let's start with scope 2. 333,000 megawatt hours, that's the amount of fuel used, multiplied by the carbon intensity, 328 kilograms of CO2 per megawatt hour, divided by that 0.92, which is the 1 minus transmission losses, and then a conversion factor from kilograms to metric tons. That's 118,000 metric tons of CO2 per year. So we're already almost at campus's level, and that's just because universities aren't very energy intensive, right? Just a few PowerPoint slides going on, not big, heavy machinery. Let's look at scope 1. On-site fuel, 97 million cubic feet of natural gas. That's equivalent to about 100,000 mega BTUs. Recall that 100 cubic feet of natural gas is a mega BTU. And so multiply that by the carbon intensity, 53.3 kilograms of CO2 per mega BTU, converting from kilograms to metric tons. That's this 1,000 factor. There's 5,300 metric tons of CO2 from natural gas combustion, and then 500 metric tons of CO2 from burning diesel fuel in all those trucks. So again, it's the amount of fuel used, 10.3 kilograms of CO2 per gallon, multiplied by those 50,000 gallons, converting to metric tons, and that's where that 500 comes from. All right, so here is scope 2, here is scope 1. Now we're getting into other scope 1 emissions. These are greenhouse gases that are emitted on site. They're just not CO2. So now we have to think about global warming potential values. So sulfur hexafluoride, 2,000 kilograms were used. You multiply that by its global warming potential value, 22,800, huge global warming potential value, metric tons of CO2 equivalent, and then a conversion factor from kilograms to metric tons. We can see that just those 2,000 kilograms of sulfur hexafluoride is responsible for 45,600 metric tons. So it grew by, again, a factor of 22,800. It's absolutely crazy. Similar analysis for the refrigerants, 5,000 kilograms of HFC multiplied by its GWP, global warming potential value of 1,430 metric tons of CO2 equivalent. Another big dent in its in carbon emissions. So again, all these refrigerants, and especially the sodium sulfur hexafluoride, way bigger than all the CO2 emitted by the trucks on site. Adding everything together, the scope 1 and 2 emissions for Stanford Linear Accelerator is 184,700 metric tons, which is greater than all of campus. And this didn't even think about scope 3, so the emissions associated with building and all the assets and equipment used on site. Okay, the rest of the slideshow is a bunch of like policy garbage that I don't care about, but if something you're into, by all means, be autodidactic and teach yourself. Canvas has the homework up. It's due not next Tuesday, but the Tuesday after. So next Tuesday, we'll look at economic analysis in lecture. And then Thursday, we'll have a super short lecture on the marginal abatement cost, which combines the carbon accounting we did today with the economic analysis we'll do Tuesday. And then we'll have a study session, work study session next Thursday to work on the homework together. And again, all this stuff is recorded, hopefully. It's Zoom Cloud. It took like 5 hours last time for them to email me my video, but it did eventually come and I posted it to Canvas. So hopefully that trend will continue. Any questions before we sign off? Let me try to find that chat window again.
So earlier when you were doing the CO2 intensity of methane, you went from the 52 grams per megajoule, and then somehow it became 55.7. I'm not sure if that's just like I can't read your hand.
Oh, yeah. You probably
or
read my...
like how did we go from that to that? I don't know if I like spaced it or whatever, but
no, you're good. Let's look at it again. So the units are a little different. Yeah, so we said 44 grams of CO2 is emitted when we burn a mole of methane. And when we burn that mole of methane, we get 890.3 kilojoules of energy.
Sure.
But this is ugly, so let's convert it to a megajoule. So we set up this ratio and proportion. We get 49.4 grams per megajoule. But it's usually reported in terms of mega BTU. And so then we went from megajoules to mega BTUs. A mega BTU is 1,055 megajoules. We get 52 point something. And it's 53, the reported value is 53 kilograms per mega BTU. So this is the same number, right? We just went through a bunch of math all over the place. You're asking where did this 55 come from?
Yes.
It's 55.7 kilograms per kilogram of natural gas. So a kilogram of natural gas is a little bit more than a mega BTU natural gas. So the difference is that the denominator is different. This is a mega BTU of gas. This is a kilogram of natural gas.
I don't know if you're gesturing somewhere on the screen, but you're just saying this and nothing is like
Oh, I
moving or
am
anything.
gesturing. I have this little pointer out. It's not.
Okay.
Let me. Maybe I can see. So this. Damn it. I feel like an idiot. That is per kilogram of natural gas, 55.7 per kilogram.
Okay.
This one is 53 kilograms CO2 per mega BTU. So these denominators are different.
Okay. But like if you transferred them, they would be the same if you switched between units. And
Yeah, if I looked
okay.
up how many kilograms of gas are per mega BTU, it's say something like 0.98 or something
And you just pulled that 55.7, you just
from the internet.
converted or from
I
the
just pulled
internet?
that from the internet.
Okay. Okay.
And this we calculated from first principles, and this is the same as that's in the stationary combustion or in the slide deck that I have from ghgprotocol.org. So this is the standard value. Sometimes people are concerned with per unit mass, and so this is the per unit mass value that I looked up from the internet. We could calculate that directly by doing something with this mass value, right? So we could say 44 grams of methane. Well, this is CO2. We'd have to go from here. 16 grams of methane makes 890 kilojoules. How many grams of methane? Or 1,000, therefore we could set up a new ratio and proportion. I don't know where I'll do this. We could say 16 grams CH4 makes 890 kilojoules. 1 kilogram of CH4 would make how many kilojoules? And then once we had that, then we could use this factor. 44 grams of CO2 emitted makes 890.3 kilojoules equals how many kilograms of CO2 per whatever this value would be, the massive amount of kilojoules we'd get from the kilogram of methane, and then this answer would equal that. It's just masturbation. You can mess around with it if you want to. It's all units and conversion factors, right?
Okay.
Um,
And
do you want me to go through it all?
I think I'm good.
Yeah.
But if I do, I will. How swamped is your email? Are you actually going to be responding to emails, or are you like drowning in emails?
It's have like 10,000 unanswered emails, but I will try to respond to yours. Um,
That's
I'm not
fair.
drowning just because I don't even swim in it, right?
You're just
Just
like,
like,
I'm just not even gonna get in the
yeah.
water.
Why would you get in that water?
I don't know. Okay. In that case, I guess I'll just make note of questions that I have for Tuesday's lecture and poke you after Tuesday's lecture because that seems like slightly more reliable
Yeah.
way to communicate at this point.
Let's just try to go through this. I think that way I'm not being lazy. Okay. I have to clear this.
I feel like it's kind of interesting that they constrain it to one like page size, even though or can you like scroll down infinitely?
Not with this. Maybe if I wrote in like Microsoft Word, this pen works really well with this app for some reason, though. I think because I can make it the size of the screen so I can map it better, but I'm being boring. Okay. So when we burn 16 grams of methane, so that's a mole of methane, we get 890 kilojoules of energy. And so what we're trying to figure out is if this value from the internet, how do I get rid of that? 55.7 kilojoules per kilogram of methane. We're trying to see if this is correct or not. So this is what we know.
Okay.
Wait, is it kilogram of methane or kilogram of CO2? This is CO2 down here. Sorry. So we're trying to see if that emission intensity is correct. And it's kind of an inverse emission intensity, right? Wait, is this methane or CO2? I forget. This is methane. I'm so sorry. Okay. Well, we'll find out if it is or not, regardless, when we go through this calculation. All right, so we burn this. So the question is, well, this definitely isn't methane because 16 grams gives this, so 1 kilogram is going to give way more. So this is CO2. Who knows what I'm doing anymore? Okay. Let me think for a second.
Are you writing more things on this?
No, I'm lost.
Okay.
I'm just thinking. I just want to know where what that value I looked up was. What that 55.7 kilojoules even is.
Because it's not methane.
Yeah. What would I even type? It's always all over the place. So there's the Mega BTU 153. Let's just start doing math and see what happens. Okay. I don't even know what the units of our answer is, but let's mess around. So I'll just ask a couple questions. How many kilojoules per burning a kilogram of methane? So we can solve that by saying 1 kilogram CH4 set up a ratio in proportion will equal X. And so X will equal...
I don't know if you did this on purpose, but you're not sharing your screen anymore.
Okay. I did not do that on purpose. Zoom. Where is my screen? Is it showing Google or something?
It's just showing the like normal grid of people's faces or empty boxes with people's
Full
names.
screen, great. Okay, thank you. Got it?
Yes.
Okay, so 16 kilograms of methane yields 890 kilojoules. How many kilojoules does 1 kilogram of methane yield? And so this is equivalent to 1,000 grams. And so we do X equals, come on, 890 times 1,000 divided by 16. I gotta open a calculator. Eight 890,123 divided by 16. So X equals 55,625 kilojoules. Oh, well, there it is. So this is 55.7 megajoules per kilogram of methane. So this is wrong, and this is the energy intensity or energy density of natural gas. Thank you for making me do this. And so this is not to be confused with the carbon intensity of natural gas, which is 52 kilograms of CO2 per mega BTU.
Brilliant. Thank you.
And if we wanted to know how much carbon this emitted, or carbon dioxide, then we would do, well, we know the stoichiometric relationship. 1 mole of methane goes to 1 mole of CO2. This is 16 grams per mole. This is 44 grams per mole, and 44 grams per mole, sorry. And so then we just set up a ratio and proportion and say that to get 55.7 megajoules of energy, we need to burn 1 kilogram of methane. Well, how much CO2 will it make? That just set up a ratio and proportion. We'll call this y to get a new variable. Would equal 16 grams per mole over 44 grams per mole. So y will equal 44 divided by 16 kilograms.
2.75.
What'd you say it was?
2.75.
Looks right to me, I guess. Yeah. Kilograms of CO2 per 55.7 megajoules. And this number you could then massage into this number, right? because a mega BTU is 3.6 gigajoules, which is a lot bigger than 55.7 megajoules, and that's why this number is a lot bigger than this number. 52 is bigger than 2.75. Whew. All right. Thank you for making me do that. That helps. Made it clear in my head. Hopefully it made it clear in your all heads. Other questions? All right, I will check my email. Canvas messages work well too. I've set up a discussion in Canvas where people can give me constructive criticism or just outright criticism. You can roast me if you want to about the online class and how to make it better. All right, let's go get lunch. See you later.
Thank you, Charlie. Bye.
My pleasure. Bye.